Alrighty. So we have a good amount to get through today. We've got our first exam next week. In this lecture, you'll be sitting here with an exam. Yes? So that's a problem with that. That's how this one works. It's a bit unfortunate, but yeah. You have to hand in your assignment, then you do the exam. So that does make it a little problematic. But I will, however, give you a practice exam, which will have solutions. All right? Okay, so we've talked about inverses. We have this magical way of doing it, this Gauss-Jordan thing, and we've explained how it works. So, this course is a mixture of figuring out how to do things, right? So you'll get mechanisms, learn how to do things, and of course explanations, right? On how understanding how all of this stuff works, and you really need to grasp all of that, so you can keep going solidly as the course progresses. Let's see. So I'm going to talk about a little bit more about inverses, what I'm going to call a small puzzle, which is sort of related through this thing here, AX equals 0. This has a special name. This is going to be a special, and I mentioned the other day, it's going to be a very special equation. AX equals B, I know you're very excited about this, but this is a really big deal. So this is called the null space equation. For some reason. Null space equation. We'll have a foreshadowing of determinants. I'll show you very strange things, determinants. I'll connect back to a problem we worked on Tuesday and show you a strange thing. Then we'll go into inverses of elimination matrices. So this is what we've done. We've taken row operations and encoded them into matrices. So that instead of saying, oh, let's do this row operation, we make a matrix that does it for us. And that gives us all this extra power. Take over the world. So, and we'll get to our first factorization. This is something I said in the first lecture. One of the big deals of linear algebra turns out to be the ability to factorize matrices. Very strange thing. But it turns out triangle times a triangle equals a rectangle. So you can always do this. Some little bits and pieces there. You can always do this. For some reason, we have these good words like elimination, and then we have identity. There are all these words floating around that are sort of okay. This is just called LU factorization, which is just a complete failure to market your product. So if we can come up with a better name, which no one in the world will understand, then we should. But we could call it triangle times a triangle equals a rectangle. All right. Okay, off we go. Let's race. All right, so there was one little piece. So we did this whole business of, right, so inverses. The Gauss-Jordan method. Gauss-Jordan method. And so we start off, we do this great thing. We say A, it's an n by n. We put an identity matrix next to it, make a giant matrix. We do row ops until we arrive. We just work away on the left-hand side until we arrive at this, and we get an a to the minus 1. Pretty amazing. And we explain why this works and how we get a nice inverse that's all happy and good. And for, let's say, the 2 by 2 example, we had this kind of thing. We had d to the minus 1, e21 minus 1, e12 minus 1 times a equals the identity. Right? So once we took our row operations and we saw them as elimination matrices, and this is the inverse of the pivot. D equals the pivot matrix. Again, this is empowering ourselves. Just what you want, right? Power. All right, okay. So once we did this, we could see, okay, this product of these weird elimination matrices and a pivot matrix, inverted, is a to the minus 1. So this is just for 2 by 2s. There's one other thing that can happen. You may need to permute the rows of A, right? So this is just an extra piece. We give a lot of examples where we don't talk about permutation to start with, but then we always have to say, you may have to do that. Yes? Oh, no minus 1. Thank you. I'm flustered. Extra piece is permutation. Thank you. Permutation, which could happen at any point. So we may have some kind of permutation matrices, right? So permutation matrices may be involved. And we call these things PIJ, right? Swaps, row I and j. All right, let's do one little example. This should work. Yeah, okay, so maybe this, 4, 4, so this is A. This is our example. 4, 4, and I have, what do I have? 0 and 3. Right, so someone hands you this thing and says, find the inverse using the Gauss-Jordan process. So we say, all right, fine. You cruel person, I will now do it. AI, stick them together, make this thing here, 4, 4, 0, 3, 1, 0, 0, 1. Oh, what have I said? No. I'm trying to start with the other thing. Gosh. Of course. Sorry. Let's get it together, human. All right. So, first thing you have to do is swap rows, right? So we have there's no pivot here. Pivot. So the first thing we do is swap row 2 and row 1. So we permute. 4, 4, 0, 3, 0, 1, 1, 0. So we've swapped those two things, and now we can go into row operations. Right, so now we don't have to eliminate this. We're good. But we have to eliminate this one here. So it's going to be row 1 prime is equal to row 1 minus something times row 2. Always this form. Always the second, this pivot here, 3 and a 4. Always the same. I know you want to try other things, but no. All right. So you can see this is a slightly tricky thing. So, but this is 4 minus 4/3 of 0. Stays the same. 4 minus 4/3 of 3. That's exactly what we wanted to get to. 0, 3. And then we have 0 minus 4/3 of this. Not so bad. And 1 minus 4/3 of 0. So that is the business right there. Last step, divide through by the pivots. Right. So this is just something we have to accommodate. And when you use programs like MATLAB and so on, they do weird, odd things, but they like to permute in strange ways, but it's always a feature. Okay, let's see. So the last thing would be row 1 prime equals 1/4 of row 1. That's this thing. And then row 2 is 1/3 of row 2 prime. So we end up with 1, 0, 0, 1. Divide through here, so we get minus 1/3, 1/4, dividing through 1/3 here, and a 0. Okay, so this is a to the minus 1. So you can check that. I could check that. You can check that. It's looking pretty good. 0, 3, yes, yes. Okay, so that's a good thing to do for yourself in your head or later. Check. So many of the problems we work on as we go through this course, we can always check. You can check, right? If you get AX equals B and you get an X, you can put it in and see if it works. That's very nice. Very nice. Okay, so that's one thing. So permuting can happen. Okay, go away. This thing goes away. This goes away. Right, so we worked on a simple example, didn't involve permuting. So example from previous. So this is a previous lecture. So here is a, has something, so this is some spookiness, okay? Going back to an example, and it was this one, we had A equals 3 minus 2 minus 2, 4. That was the one we worked on. we worked through this and we found out that a to the minus 1 is, and I pulled out an 8, right, just to clean it up. But there was actually a bit of a stronger reason. 4, 2, 2, 3. Secrets, weird things, weird things. So let me tell you an odd thing. This is a foreshadowing of about 5, 6 weeks away from now. Okay, so here's A. Let's take A, and it's got these vectors in here, right? This is A1, the column vectors in here, A1 and A2. So let's do something odd. We're going to plot these. Let me get this right. So they're going to look, they're a bit funny looking. So there's one, so A1 is 3 out here. So let's make a nice looking thing. It's not too messed up. 1, 2, 3. So this is A1, 3, and it goes down to minus 2. This is A1, 3 minus 2. This is in, so the column vectors are always in Y space. So we'll keep saying this. They're always in Y space. That's a bit of a, what we're going to call Y space. Okay, so there's A1. This is really nuts thing. Okay, that, and where's our other one? It's minus 2, 4. So minus 2 and then 4. 1, 2, 3, 4. So we're here. Right. That's A2. Minus 2, 4. All right, good. So let's do something odd. Let's make a parallelogram out of this. Right, we've got these guys here. And if we added 3 minus 2 to this one, so we're going to add 3, so we go over here and down to here. Look like this. Right, so this is A, I'm adding A1 here. That's that guy. And then this one is A2. So we've made a little parallelogram. It's a little thin parallelogram. Okay. Form. And this really is nuts. Parallelogram. Parallelogram. Okay, good. Yes. So let's, what's the area of a parallelogram? That's kind of hard. So we'll draw a box around it. I draw a box here, explode the chalk, and we go across here, down to about here. All right. So the area of our parallelogram, so it's the area of this whole box, and then I'm going to subtract off the area of this guy, and 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 this guy. Let's do that. One way to do it, all right? So the length here is, what is it? It's 2. This is 2. The length here is 4. This is a 2. Actually, this part here is a 3. I'm going to have that triangle. This length is, it's a 1, so this is 2. 2 here, 2 here. And that length is, what's that one? Minus 2, it's another 4. Yeah, good. Has to be. So the area is the whole area, which is, it's a 6 by 5. 6 by 5, so the area of this is 30. And we're going to subtract off these things. So there's this area of that triangle. There's minus this one as well, so they match each other, minus the area of the 2 boxes, the little boxes, and minus this area. Yeah, this is really silly. These ones you can join together, right? So there'd be a 4 by 2, 4 by 3 box, 4 by 2 box, 4 by 2 box. Yeah. So there's 8 here. If you look at this, this is a minus 8. You can check this later on. That's a minus 8. These things are 3 by 2, so that should be a minus 6 for all of that. These are blocks of 4, so minus 4 here, minus 4 here. So it's 30, minus 8, minus 6, minus 8. What's that? Just hacking my way through a terrible calculation. 8? It's 8. So the area of that beast there is the same as this thing. Now I did just pull an 8 out here, but it is a very special, there's a special reason for pulling that 8. You pull out 16, you can pull out 4, whatever you want. But this is the area of the parallelogram created by these two column vectors. All right, we'll come back to that. Created by A1 and A2. So there's a deep geometric meaning. And so when you go up to higher dimensions, you have parallelepipeds of 73 dimensions. So, in all these matrices, right, there are all these inside pieces that you can't see that you start to, we're uncovering slowly. All right. I wanted to tell you that. All right. Okay. So, let's, yeah, we'll not do the puzzle. Let's talk about inverses of elimination matrices. That's why I was excited about that over there. And, which I don't think we talked about. Did we talk about that? No? Elimination matrices, inverses, did we do that? I don't trust my brain. Okay, so, all right. Inverses, so this is where we start on today's work. This is a couple, well, that's a patch up from last time. This is just a little more insight about what's going to happen later on. Matrices, and, well, let's do these guys first. And row, well, we'll call them row swap. Permutation matrices. Okay. Good. Let's do this. So here's a E31, for example. Here's an example. This guy, 1, 0, 0, 0, 1, 0. Looks mostly like the identity. It's got a -2 here. This is, I'm just making this one up. So we need to go back. This is a row swap thing, right? So this is, I'm sorry, no row swap. This is a row operation. So this is equivalent to saying row 3 prime is row 3 minus 2 times row 1. So what would be a way to undo this? How do we undo this? And I'll tell you there's two other things we never mention here, right? Which is that also row 2 prime is equal to row 2, and row 1 prime is equal to row 1. So they're not changed, right? So this one says, this thing here says row 1 prime is row 1. Don't change it. You have to think about how this thing works when it multiplies another matrix or vector over here. It says I want 1 of the first piece and then 0 of the others. Looks like the identity, right? And then the next line says I want, just give me back row 2. Right? 0 of row 1, 0 of row 3, 1 of row 2. And then this one is doing the work. This is the row operation. Row 3 minus 2 times row 1. Right? I want row 3, I don't want any of row 2, and I want to take away 2 of row 1. Way to read this. So what's a way to undo what this thing does? What do you have to do to undo it? We undo with what kind of row operation? Do we need to do anything to row 2 to get it back to the old row 2? Right? We haven't changed it. Row 1 is still the same. Row 3 was changed. Row 3 was changed because we subtracted 2 of row 1 from it. But we still got a copy of row 1. Row 1 hasn't changed. So we can, yes, we just do the opposite. So let me write them in the right order. We'll just say row 1 prime is row 1, row 2 prime is row 2, and row 3 prime is row 3, and it's going to be plus 2 times row 1. So this is, let me get back over to another board. This is a beautiful moment, Because we worked very hard on our inverses, because I wanted to tell you all about inverses, so we just did that. But now we don't have to, it's a funny noise. We don't have to do all these, for elimination matrices, we don't have to do this. We're not going to have to do this. We're just going to know what the inverses are, because we can tell the story of how these little gadgets function. So, elimination matrix 3-1, its inverse is going to look exactly the same. Everything's the same, and we just put in +2. We just swap the sign of this guy here, +2. +2. So, there was a sneaky thing that we did from the start. The way we've constructed these things all along, there's a minus sign here in these row operations, minus sign, right? We did this kind of perverse thing. It was sort of okay, we're subtracting something from, but we could have made that a plus. So there was a reason for that, because of monks. Not completely in general, but in general, we have this sort of thing, E31, 1, 1, 1, 0, 0, 0, 0, 0. This is what we called minus L31. This is the multiplier. Right, it has a pivot on the bottom of it, and it had a minus sign sitting here. So if that's always the form of these things, then E31, the inverse of it, is now going to look exactly like the identity, but it has a plus L31. There's another 0. And it's better to have a plus over here. We're going to come to why that is, but the plus is a nice thing here. And there's a reason it's a small L. All right, so we're kind of just opening something up here. So, very easy. If someone gives you an elimination matrix and they say, what's the inverse of it? You just flip the sign of the off-diagonal entry, whatever it is. Easy. So straight away, you can say the inverse of this guy, let's say E, well, let me write down 1. 1, 1, 1, 1. Let's make a horrible looking thing. -7 in there. Sneak that in. What's this guy actually? E, what's the subscript? E32, right? So row 3 is here. That's this piece, and then this is column 2. So it's so this is cleaning up row 3 using row 2. That's what this is doing in a 4x4 system, or in a system of 4 equations. Okay. So straight away, in this case, E32 minus 1. We just flip the sign of that thing. So 1, 1, 1. All of these guys looks just like the identity. Boom, 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 boom. And we get a +7. And then another 0. Close box. Numbers in boxes. That's it. So that's super easy. You can't do this in general, right? If there are a couple of numbers in here, just calm down. You can't generalize this. This is a very special thing. And you can go back again and again and look at what the row operations are doing and see that they have a simple action, and that the inverse of that is a simple action, and then you can encode that straight away. You can just put it straight back in. All right, so that's good. There's also eliminate, well, I guess we'll do it. We'll do it, all right. In general, simple inverses for permutation matrices. And let's call them row swap. Row swap matrices, really a special case of permutation. Right? We could permute everything, and also we could jumble everything, but we'll denote them as they're really row swap. We're only swapping I and j. So let's see. So this one, for example, we'll call this one P23. So what does this do? It encodes the row swap 2 and 3, right? Because read across what it says. Let's write. So this is useful now. We haven't done this before. We're going to say this. This is saying row 1 prime is row 1. It's giving us information there. We didn't write that down before, but we are. Now, this is saying row 2 prime. The new row 2 is 0 of row 1, 0 of row 2, 1 of row 3. So it is row 3. And the new row 3 is 0 of row 1, 0 of row 3, but it's all of row 2. So this is a direct swap. So the inverse of this guy, what's the inverse of this one? What do we do? So if we swap these two rows, so what happens if what's it look like if we swap these two rows? Because it feels like, you're right, it feels like you might be able to do that. If we swap those two, it's going to be the identity, actually. So that's going to leave it unchanged. It's itself, actually. Yeah, this is a sneaky business. Yeah. So P23 minus 1 equals P23. So very reasonable path to take, but it turns out it's this. Because it says swap row 2 and 3, and because you haven't obliterated them, you haven't messed with row 2, you've just put it in another box. So you can pull it out of that box and put it back in its original box, and the same for P3. You haven't added them and messed them up and multiplied them by things, right? So the information hasn't been lost. So in general, permutation, the inverse of a permutation matrix where we're swapping lots of rows, swapping many rows at once. I'm just going to sort of put this at the side. This is just sort of a side thing, is equal to this thing, P transpose, which is our next topic. All right, so more later on that. Okay. All right, let's get this to work. Right, we've been doing lots and lots of things, lots of push-ups, and now we might be able to throw a ball or something. Okay. I don't want to promise too much. Okay. So let's do our first factorization. Yes, good, good. And you can look in the book, you can look on Wikipedia. There's tons of factorizations, whole zoology of factorizations, right? And it depends on the job in front of you. We're interested in this AX equals B thing because you all came in here asking me about AX equals, no, because I'm telling you should do it. And it turns out this is the factorization that helps immediately with that. Okay, so our first factorization. It's an emotional moment. Factorization, right? So just like you do with like factor, and 14 is 2 times 7. We're factoring it, or we factor it, right? That's the same idea. There's also decomposition. You sometimes hear that too, I think. Do they? All right, factorization is a good word. It's going to be A equals LU, and I'm just going to put a little sort of an important note here, but truly it's this, actually. It's P, some permutation of A, permute. So we have to figure out the right permutation of A, permute the rows. So once we've shuffled the rows around properly, then we can do this. All right. So this is going to be, this line here, this is true fact. This is not, so we'll have some factorizations that only work for square matrices and some that only work for certain matrices that have special properties. This one works for every matrix, which is exciting. Okay? So this is a universal, works for all matrices. So that's cool. That's a good thing. Rectangles as well. And let me say, And I'm just going to sort of drop this for a while because it'll be just sort of useful to deal with a simpler one to start with. So we'll kind of leave P off for a while, for a start. Let's just imagine we don't have to do that. Okay, so the shape of this, let me tell you what this is. This is going to be an m by n. This thing is an m by m, so this is a square, and this is an m by n. So it's really that A and U are they're the kind of similar beasts. And this is going to be a combining matrix. And this guy is going to contain the sort of essence of A. A kind of essence of A, right? Lots of essences. So it's A-like. You can make A with this thing. And moreover, they will be lower triangular and upper triangular, hence this ridiculously lame branding. I mean, they could have called it, I don't know, Destroyer of Worlds or something. But anyway, so we've got that. So L is lower triangular. I'm just telling you these things. We're going to get into an example. U, which we've been getting at, of course, so we know U. Upper triangular. So this is from before, right from before. This is new. This is the new piece here. Right, we went from AX equals B to UX equals C, and we noticed that upper triangular systems are easier to solve. So are lower triangular systems. Okay, I'll define, we'll get these things as we go along. But generally speaking, roughly speaking, it's going to look like this. It's all zeros up here, 1, 1, 1, 1, stuff. Square, m by m. This one is going to be it's going to be pivot 1, pivot 2, pivot m. Not always exactly like this, but roughly. Zeros here, stuff. Roughly. They're our boxes, okay? So this notation here means there's a little stair step down here. Boop, boop, boop. Echelon thing, zeros, zeros. All right, let's get an example. Yeah, so let's recall our mission. Right, so shoot a tiny little torpedo down a small hole in a lot. No, it's not that. Okay. It's a mission of different nature. Okay, so AX equals B. Solve AX equals B. What I'm going to show you is if we're going to do this equation over and over again, and we're going to change B a lot, for some reason we change B a lot, we really have A, we're going to change B a lot, it's good to create this LU business. Right. Okay, so let's do our thing. Let's have an example. Yep, this is our mission. This is our mission. And again, this is known, unknown, known. That's how it works. So here is an example we're going to work through. Solve this, x1 plus x2 plus x3 equals 5. So we'll start with the barest version of it, x1, 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 written in terms of equations. 2x2 plus 3x3, let's do this, it's great. All right, plus, delicious. It's really, really nice. Okay, equals, I know that's what you're thinking, I'm just saying it out loud for you. Okay, so equals 11, all right. Goody. Okay, so this is presented to you, and you are very happy. This is a 3x3 system, right? That's equations, unknowns. It's the shape of our box. This is the row picture. row picture. We're going to, of course, turn it into this matrix picture. And coming back again will be the column picture. That's the next section. All right. Yeah, it's dead. All right. Okay. Yeah, I give up. Okay, we are here. Right. So you remember we had back substitution, now we're going to have back substitution and forward substitution. That's what's going to happen. All right, so let's do it. Okay, got an example, I'll leave it over there so I don't destroy myself too much. Oh, I'm erasing the wrong things. Okay, good. But they will die. Yep. Okay, that's too much. Oh my God, I can't erase it. My weak little arms. Okay. All right, let's do it. Let's just, for fun, we'll write down the column picture. Right? What does that look like? It's x1, just so we see we're trying to add this vector, some multiple of this vector, to some multiple of this vector. Right? Viola, kazoo, and the accordion, the dreaded accordion. And we want that to make this sound over here, 5. All right, let's do it. So that's the column picture, or this. And then the matrix version is this. We'll just write it straight down. We're into this. 1, 1, 1, 1, 2, 3, 1, 3, 6. So I got it right, 1, 3, 6. And I'll just put it straight into augmented form. No, you know I won't. I'll put it x equals 5, 7, 11. And so now we're here at A, X, B. All right, so let's do our row operation. We're going to work through this monster of a thing. It's not that bad. We have to do three row operations, right? We're aiming for this shape here. And our row operations will give us this magical thing. All right, so first thing, let's do it. Let's just work on all right, we'll do the whole thing. So, row 2 prime equals row 2 minus something times row 1. That something is 1 divided by 1, or 1 divided by 1. Now we can actually do 2 row operations. We can actually always do these together. So let's jump ahead a little bit. We can change row 2 and row 3 because we're using row 1 to clean them up. So let's do that, and again it's 1 divided by 1 times row 1. So all of that gives us this system, so I'm going to subtract the first row off, the second row, and the third row. You can see that's obviously the thing to do anyway. But nevertheless, we always use our very principled structure. So let me write this, let me indicate these things. This is L21, and this is L31. If you can read that. L21 and L31. So far we have this. 1, L31 equals 1, and the pivot, first pivot is 1. That's what we can see so far. We can't see the second pivot or the third pivot. So let me note that. That's really important. So hidden is L32, D2, and D3. You cannot see those things. So we're going to subtract that first row from this row, so 1, 1, 1 off here, so we get 0, 1, 2, and we get 0, 2, 5. Good. And we're subtracting the first row off here, so 7 minus 5 is 2, and 11 minus 5 is, is 6. Okay, good. One more step. So row 3 prime is row 3 minus something times row 2. And whatever is in here is L3, 2. So it's 2 divided by 1. 2 divided by 1. And now we have, at this point, we also have the pivot D2 is equal to 1, and L3, 2 equals 2. At this point, we can write these things down. So how does that change our matrix? We have the same top row. We have the same second row, 0, 1, 2. Down here, this is a 2. And I'm subtracting 2 times the second row from the third one. So that's 0, 0, 1, 2. 0, 0, 1. Did I get that right? Okay. All right. Yeah, okay. All right, so the pivots are not very interesting, but there you go. That's what we've got. You know pivots can have all sorts of values. This is D3 equals 1. So everything's now been uncovered. We've got our 3 pivots, and we've got the 3 multipliers. And we've got U. Right, so this is upper triangular. It's got zeros below this main diagonal. And we called this whole system, this is U, X equals C. Right, so this is, so triangular systems are easy to solve. Easy, so this is a big deal. This is a big deal, number 72. Triangular systems are, there's no ordering scheme. Triangular systems are easy to solve, right? In the past we've used back substitution, right? That's how we set this thing up. Once we've got it, we use back substitution. All right, let's get this right. Right, because we have this last equation is just x3 equals 2. Read it off. Then you substitute it into here, and you get x2. And then you substitute both those guys in here, and you get it. Yep, good. We use back substitution. Easy. Easy. All right. Yes. So let's put things together here. So we had elimination matrices. Let's write down what they were. So, right, our elimination matrices are these things, right? So there's an E21. Well, you should write them down. E31 and E32. A lot of space there. Write them down. Okay, so they're going to look like the identity matrix mostly, except for their one special place. Special here, right? This guy's all identity, this one too. So you should have, unless I've got this horribly wrong, -1, and a -2. 1, 1, 2. So these guys are L21, it's a minus L21 there, minus L31, minus L32. So to get to C, to get to U, this is what we do. We apply these things, right? So we can think of it like this. E32, E31, E21 times A equals U, right? This is our row ups as matrices. So the new idea, so we did this before, and so we did this as well as this too. We actually applied this to the other side, E31, E32. We did this to B to get C. right? That's our row ups expressed as matrix operations. Okay, so the new idea is this. Because we've been able to, row ups, very nice things. These elimination matrices do the same things, but if we want to sort of combine that row operation with that row operation with that row operation, it's not so obvious. But when we're dealing with matrices, we're just multiplying them together. It makes it a simpler, if still complicated, thing to do. So we can take this equation here and we can put all the elimination matrices on the other side. So we're going to start peeling them off, putting them over here, and we'll get A is something times U. And the magical story is it will be a lower triangular matrix. And that's not obvious, but it will be. So unwrap this first equation to get A equals something times U. So it's okay, let's yeah, right. Yes, it is. So what's the first one? So it's E. There's going to be an E, an E, an E, minus 1, minus 1, minus 1. What's that one there? 2, 1. Very good. All right. So it's just like we said the other day. The inverse of all of this is the reverse of their inverses. Right? So you have to undo them one at a time. So we're going to multiply by the inverse of E32. That's going to get rid of this one. And then we'd have to peel off this one, inverse of E31, inverse of E21. So the order is reversed. Note. Order reverses. Right, you have to undo them. The last one you did, you have to undo it. Then you have to undo the next one. Okay, good. All right, so that should be just some schmozzle times U. I mean, that's not obvious that that's going to be anything good. So sad. But we do know one thing already. So we already know that that the e to the minus 1 is easy to find. Right, that was the thing we did at the start. We just swapped the sign of the off-diagonal element. Right, just swap the sign of the minus Lij piece element. So we can just write them down here. We're going to have the inverse of E21, the inverse of E31, the inverse of E32. We're just going to swap these signs. We've argued for why that works. So E21, inverse, E31, inverse, and E32 inverse. Again, they look like the identity matrix, but it's and I'll use a different chalk. They look mostly like the identity matrix. Zeros. And this is another one with lots of zeros. Zeros, zeros, and then inside of these things we have a +1, a +1, and a +2. +1, +1, and +2. So this is, in general, plus L 32, and this is plus L 31, and this is plus L 21. So the ridiculous choice of a minus sign is being, there was a reason, right? Because we knew where we were going. Still, this is a bit odd. We have to multiply these things together. So that could make a big knot, right? That could make a horrible thing. Multiplying matrices together, usually stuff goes all over the place. Incredibly, that is not true here. Okay, so we've got our things. Good, good, good. So we've made a couple of observations. The elimination matrices, their inverses are easy to figure out. There's also some other aspect about them that's maybe a bit less subtle, but or more subtle, is that Elimination matrices are lower triangular. Just barely, but they're lower triangular, right? They have zeros above the diagonal, and they have one of these guys hanging around. So you have to say these are lower triangular. So let's call this observation, whatever number you want. I'm just making these up. Number 17. It's a good random number. 17. The E's and the E, e to the minus 1s, are all lower triangular. Just a note. I promised a lower triangular shape. So that's useful. Okay. Let's put this up here. Good, good, good. So a very weird thing is going to happen. The multiplication of these matrices is pretty much unlike any other matrix multiplication in that it does something very simple that you would not expect, and I'm going to argue as to why you should expect it after you've seen it, which is why the word obvious and trivial and so on should be banned from the English language, because nothing is really like that. All right, so they're easy. They're lower triangular. Let's do a multiplication. Okay, so E, let's multiply these things together. E21 minus 1 let's do it. Okay, let's do this. And we'll do it for abstract ones, right? So we'll 1, 1, 1. And this is, as I've argued, this is L21. This seems like a funny thing to do. Let's just struggle through this. L31, 0, 0, 0. And then this is L32, 1, 1, 1, 0, 0, 0, 0, 0. Good. We got this right? Yeah. So let's do these two first. We're going to multiply these together. So I'm going to leave this one here. 1, 0, 0. There's an L21. 1, 0, 0, 0, 1. This is very strange. Let's multiply these things. So you can keep thinking in this way, right? 1, 0, 0 says I just want one of the first row, right? This multiplication, instead of tiny little dot products, 1, 0, 0, it says give me one of this first row, 0 of this, 0 of this. So let's do that. First row is just 1, 0, 0. 0, 1, 0 says I want just the second row. And this one says L31, I want L31 times this row plus 1 times the last row. So what's that? So I'm trying to have a slightly more elevated way of thinking of multiplication, right? This row multiplied with this matrix here says I want L31 of the first row, 0 of that row, and 1 of the last row. So what have I got here? L32, I think. 3, 1. Good. Good. And 1. Kind of weird. Let's do one more. Now we're going to multiply these guys together. Again, this says I just want the first row. Just take the first row, 0 of the next one, 0 of the next one. Like that. So the first row is just 1, 0, 0. This one says, well, let's look at the bottom one. What does this say? It says 0 of the first row, 0 of the second row, 1 of the last row. So just don't change it, right? This is an identity matrix piece here. So just this row gets copied straight across. This row gets copied straight across. So it's L31, L32, 1. And the middle one says, well, I want L21 of this row plus the middle row. Just one of the middle row. None of the last row. Right, so L21 times this row is L21, 0, 0, and then 0, 1, 0. So that turns out to be like this. So that's very strange, or kind of nice, because look, now we have a lower triangular matrix. And some of you have noticed as we've been going along, at least much more inside your heads as well, but there's been some mentions of the fact that these indices are in the right spot, right? So row 2, column 1, row 3, column 1, row 3, column 2. So L2, 1, L3, 2. So when we assigned these letters, L, this little L, and we assigned these numbers, there was a reason. And it turns out that this is how these matrices always form, and we're going to explain it. It's an L. It's a lower triangular matrix. It's L, and the multipliers live here. They live in, so these are the multipliers. From row ups, they've all got plus signs in front of them. From row ups, you always have ones on the diagonal. Ones on diagonal, main diagonal. So that's the anatomy of an L matrix. This example we did is a little bit funny because the U is not as complicated as it could be. But now we can write this. A equals L times U. Right? So, well, right, let's do it. So we have, in our case, it was, it's up there, 1, 1, 1, 1, 2, 3, 1, 3, 6. This is our A. And we'll just fill in the multipliers. 0, 0, 0. And the U we uncovered, U is up. Where is U? U is up there, 1, 1, 1, 1, 2, 1. There it is. Has zeros below diagonal, and we had 1, 1, and 2 for these guys. Right? This is A, this is L, and this is U. So we've gone crazy. Why do we do this? In general, this is m by n. It's a square in this case, but in general, it's this. This is always a square, and this is m by n. So, as I said at the start, this is a combining matrix. It tells you how to combine the rows of U to make the rows of A. So L tells you combine the rows of U to form A. Right? And U's rows are much simpler. They're much simpler, right? They always have this upper triangular structure, so they're much simpler. They're not at right angles to each other, which is something we'll talk about later on, but they're easy to work with. So let's do it for our example. Yep. And I may have to do the explanation depending on how we go. We'll see how far we get. All right, so if we have A equals LU from the start, so given we know A equals LU, right? So we've worked hard to do this. No B, right? B is not involved, right? So there's no B involved. There are no X's. This is just something where we go on this little row operation festival. We get the multipliers out. And I'll show you this always works, by the way. We'll get to that. We've done just this one example. So given we know this, then the problem, then AX equals B becomes this, becomes LU, we'll replace A with X equals B. And if we want, we can say, all right, well, let's call this is a vector, right? This is m by m. This is m by n, m by 1. And this is an m by 1. So this whole thing in here is an m by 1. we can solve the problem L times blob equals B first. This is where it's truly exciting for you, right? So instead of trying to mess around with this A thing anymore, we've turned A into two triangles, and we solve two triangular systems in a row. Right? So we now solve two triangular systems. That's the big deal. Systems to find x. So let's call this thing in the middle, just as we have. We've been saying ux equals c, right? So that's what we have. So we solve LC equals B. So we start with this. So it's often just good form to find LU, but if you're going to be changing B a lot, you can see why this will be very, very simple or helpful. All right. So let's do it. We have an L. It's this guy. So now we have this problem, 1, 0, 0, and it's 1, 1, 2, 1, 0, 1. Read that. This is times C1, C2, C3 equals, and our B, right? Our B is from the original problem. It's 5, 7, 11. So if you can see this underneath the palimpsest situation, this is lower triangular. So we solve it not by back substitution, but by forward substitution. All right, good. So we start at the top. So instead of starting at the bottom, we start at the top. So the first equation, so we go back out to equations, right? So the first row, row 1, is what's it telling us? It's telling us that x1 plus 0 times, well, c1, I should. c1 plus, these are just zeros, equals 5. So c1 equals 5. Done. Super duper. The second row, c1, see if you can write that down. C1 is what? C1, what's the second row say? 7, all right. So we've got this. We just substitute C1 into it. So we've got 5 plus C2 equals 7, which gives us, so this. So C2 equals 2. Goody? And then last is row 3, so we're moving down, and we have C1 plus C2, C2, 2C2, plus C3 equals 11. And this, we substitute our pieces in. We've got a 5 plus 2 times 2 plus C3 equals 11. Right, so this is 9, C3 equals 2. So we have to look, we need to concentrate a little bit sometimes. It's easy to sort of turn this list of numbers upside down. C1, C2, C3, that vector, C, is now equal to, we've seen it, it's 5, 2, 2. So this is a very easy procedure. Once you've done all the hard work of turning A into LU, right, finding this triangular structure. So this is kind of, I think it's amazing. You can do this all the time. It's not obvious. It's not very cool. I'm sure it's not cool. Okay. It's just awesome. All right. Okay, let's see. All right. So that's step 1. And now we go to back substitution, because ux equals c. We just found, right? This is what we're saying. This is ux equals c. Now we've got c. So next is back substitution. So ux equals c. And our u is, what is our u? It's 1, 1, 1, and then a 1, 1, 2, 0, 0. Is that right? And this is multiplying x1, x2, x3. We're trying to get to our goal here, and this was 5, 2, 2. Did I get that right? Short-term memory. All right. Excellent. Good. Good. So let's do our back substitution. Now we go upwards, right? So row 3 in this case tells us that x3 is equal to 2 straight away. Row 2 says x2 plus 2x3. You should absolutely be able to do this thing cold, right? This is definitely something you should, and of course understand it, which we'll come to on Tuesday a little more. x2 plus 2x3 equals 2. We've got our x3 in here, so we're going to put it in. So that's plus 4 equals 2. So that gives us x2 equals minus 2. And then row 1, finally, they all add up to give you 5. x1 plus x2 plus x3 equals 5. It's sort of an aside, right? But if you have a row of 1s, what that's saying is sum up the vector, actually. I want one of this one, one of this one, one of this one. It's a sum. That's a sum thing. Okay. x1 plus this, blah, blah, blah. It's 5, so there's a minus 2 for x2. x3 was equal to 2. And x1 is equal to, x1 is there, and this is equal to 5. So these cancel. x1 equals 5. This is where we need to be careful. x equals x1, x2, x3 equals 5 minus 2, 2. All right, so you see the plan. So all these things you've done before. You've done back substitution. Now forward substitution is just the reverse of that. But there's work to be done in getting the LU structure out, and we haven't finished everything about this. The overall story is that we can always do it. We may have to permute the matrix A a little bit to start with. And let's see if I can explain why. Why would this work? So let me quickly write some things here. So we go from AX equals B to U x equals c. And this direction, this takes work. So this takes work. Can you read that? It takes work. Right? These are our row operations. This is easy. It's easy. I mean, we sort of showed this is easy. This is an easy thing. The U, they come from A, of course. They're based on A. But these rows are simple. They have a simple structure to them, and you build up A in an easy way. So that's sort of roughly a story here. But let's say the right things. Right. So why is this? So let me write it like this. So, and I'll come back to this, but let me write this one. So row 1 of A is equal to row 1 of U. It's 1 times row 1 of U. Right? That's part of our something that's coming out of L. Row 2 of A is equal to L21 times row 1 of U plus 1 times row 2 of U. And this is just for a 3 by 3, or a system of 3 equations. Row 3 of A is equal to L31 times row 1 of U plus L32 times row 2 of you. Yeah. And plus 1 times row 3 of you. So the rows of A are built simply out of the rows of U, and it's not true the other way around. And I'll come back to that and explain that in more depth on Tuesday. All right, so assignment 3 is up. Exam 1 is next week. Work hard. Okay, thank you.